Welcome to AI with Sally, a podcast that takes a closer look at some of the most interesting technology stories on artificial intelligence and machine learning. We'll hear about the latest in hardware and software that has a big impact on the world of AI. I'm your host, Sally Ward-Foxton. Welcome back to AI with Sally. Today's episode is brought to you by Lemurian Labs, makers of a full AI stack that lets you keep performance and swap out hardware, port workloads across CPU, GPU, and NPUs, and simplify developers' workflows, letting developers get back to creating cool stuff. I'll be chatting with Lemurian CEO Jay Dawani later in this episode, but first, here are some news stories you may have missed from eetimes.com. Big news this month. British AI chip startup Graphcore has been acquired by SoftBank. After much speculation, we finally have at least some details. Graphcore confirmed the company was purchased for less than the $700 million that had been invested in it, although we don't know the exact financial details of the transaction. We do know that Graphcore will continue to operate as a division of SoftBank and will keep the name Graphcore. I have plenty of details about this story at eetimes.com. Longtime IP company MIPS is now targeting AI applications for its application-specific data movement cores. Efficient data movement is, of course, critical to AI applications, and MIPS is hoping to replace proprietary cores in data center and automotive applications. I had a chat with new MIPS CEO Samir Wasson about how to pivot to RISC-V and how to pivot to AI applications while keeping the MIPSiness in MIPS. You can read that interview with Samir Wasson at eetimes.com. I went to visit automotive chip company Ambarella again recently and was able to see their new demos of multimodal LLMs running on the new N1 chip. This includes Lava 34B, which I was able to see running live. I also had a long talk with Ambarella CTO Les Cohn about multimodal LLMs, which he says are ready for L3 autonomy in vehicles. He said that because they have a more general worldview, they're better able to deal with complex, long-tail scenarios encountered in the real world. The full-length interview you can read at eetimes.com. Before we get to the interview, I wanted to give a little shout out to the AI Hardware and Edge AI Summit, which is September 9th to 12th in San Jose. They're expecting at least 1,200 attendees from the AI infrastructure and semiconductor industries, and I'll be there in person moderating a panel too. Today's podcast guest, Lemurian's Jay Dawani, will also be presenting on the Tuesday afternoon, so make sure you don't miss that one. You can get tickets at aihwedgesummit.com. Lemurian Labs is an AI startup led by CEO Jay Dawani. Last time Jay and I spoke, Lemurian was working on custom silicon for the new log number format the company had invented, but it's definitely time for an update. Jay and I started off talking about the problems AI rollouts facing with the amount of available compute and exactly how big the gap is between supply and demand. I also asked Jay about how much of that gap can be closed by hardware, how much by software, and how much by more efficient models and other techniques. Have a listen to our fascinating conversation. Welcome to the show, Jay.
Thank you for having me.
So I think viewers of this podcast, or anybody who listens to this podcast, anybody who reads E-Times, or anybody that hasn't been living under a rock will know that transformers and LLMs have become a really big deal. But these are really huge models and it needs a lot of compute, a lot of memory, and a lot of infrastructure. And as we transition from kind of training to inference at scale, we're going to need a lot of data centers for this, right? Tell us about the scale of the problem we're facing here.
Yeah, absolutely. First of all, every time somebody says transformers are a big deal, I always think for a moment Michael Bay's and they're getting super happy and they get disappointed when he learns it's not that transformer.
It's not that transformer today, no.
But yeah, I mean, if you look at AI fundamentally, or just neural networks, the thing that's so appealing about them, they're a very regular structure, right? Regular structures get accelerated. They can scale well. That's one of the magnificent parts of this particular kind of a workload, right? When you think of neural networks, there's really three things that matter. There's an inductive bias, there's a prior, and there's scaling. And if you have enough data and you have an algorithm that can scale and leverage compute, it's going to get better and better over time. And the more you scale it, the less you need an inductive bias or a prior because data does a lot of that job for you, right? And that means you need a neural network that can exploit some of that data. Right? Transformers are really good inductive bias on, and are general enough so that they can leverage different kinds of data as long as they're tokenized. So that's one of the great parts of it. Convolutional networks have a limit to scaling. transformers came about because RNNs could not map well to GPUs, right? But they were explicitly designed to leverage parallel compute.
Yeah.
That was the whole point.
Yeah.
And if you can scale it, you have a lot of capacity, and a lot of capacity and degrees of freedom means you can learn a lot about the different properties of the underlying data, right? And that's currently what we're saying. And we find that every time we throw a little bit more compute and a little bit more data, we get a whole new capability that we weren't expecting. So it's kind of magical in a lot of ways. And, we weren't really expecting the scale at which things are currently going. At least some of us didn't. Back in early 2018, I was working on multi-billion parameter networks. So some of the very, very early ones. And I don't think I could have ever said we'll be operating in the trillion parameter scale. That I still struggle sometimes thinking about that. Like, how would we get here?
Yeah.
But the crazier part is we're still in the steam engine days, and we have a long, long way to go. I don't think that transformers would be the last architecture we ever built. I think we can always do better, right? And we're still learning. And algorithms generally have to get redesigned because, when you're looking at systems, incommensurate scaling is a real thing. Different parts of a system will scale differently, and it'll break at some point, and you have to redesign it and rethink it. We're partly already there, and a lot of people in the industry are saying it. But to give you rough orders of magnitude, right? We're currently in the range of requiring anywhere between 10 to the 27 to 10 to the 30 flops for training.
Okay.
Right. Those are obscene numbers.
Obscene.
Right?
Okay.
It wasn't that long ago that we thought petascale supercomputers were a big deal.
Yeah.
Right. Now, in the span of 2 decades or less, we're talking about zettascale machines.
Yeah.
To train the next generation of models.
Yeah.
Right? A zettascale machine based on current technology out there is around 12 to 13 nuclear reactors. Or 12 to 13 gigawatts.
Yep.
Right? Building that campus, finding that land, getting it all ready. We're not there.
We're not. Do you think this is kind of holding back development of transformers? Transformers just want to get bigger and bigger, right? Do you think this is holding us back?
Yeah, I think that's what's holding us back. I think this is where things get really interesting.
Okay.
Right? When you're thinking about systems, you have a lot of different moving parts. And it's also what's really challenging about them. They have nonlinear impacts. When you tweak one part of the system, they have a whole different kind of impact that you weren't expecting. Right? There's a limit to how far physics can take you. There's a limit to how far cleverness can take you. There's a limit to how big it works, the kind of algorithms you can come up that can leverage kind of compute and scale.
Mm-hmm.
Like historically, I think we've only found 2.
Okay.
Truly that work, at least for AI. That's a matmul with a gradient descent. So basically what we have neural networks. So gradient-based learning and search.
Okay.
Like learning and search are the 2 things that scale.
Okay.
Right? Because they can leverage compute and data. But it comes down to the organization of work and how well that maps to the data. If you can do that well, you can continue to scale because you reset yourself in a certain way.
Okay.
Right? So think of it this way. I could make a fully connected network, 1,000x bigger than a transformer, and it would roughly do the same job.
Okay.
Right? So having that algorithm saved you a whole lot of compute. So it stands to reason that if you come up with better algorithms, they can have a similar impact. And if you do that, you're better leveraging data because you're more sample efficient and you are scaling better.
Okay.
Right? So you kind of need the combination of those things.
Yeah.
And eventually you get to a place where you don't just need hardware software co-design. You need algorithm software, hardware software co-design, packaging, triplets, heterogeneous computing, and entire supercomputer co-design.
Yeah. I know you said we don't just need hardware software co-design, but that would be a good start, right?
Yeah. It's always a good start.
That would be a great place to start. Yeah. I mean, where is all of this compute going to come from that we're going to need? 12 to 13 gigawatts to scale computers. I mean, this is not really going to be possible. There's something's got to give, right?
Yeah. So the fun part is, at least to me, if you do a bottom-up calculation and you design an accelerator again from first principles, you can actually get, 25 petaops in 700 to 800 watts.
Yeah.
Right. Maybe more. Right. So there's a limit to how good things can get. A thing is roughly 2 picojoules per op. And once you get, that's sort of the limit for general purpose acceleration. Right. Then you have to go towards heterogeneity.
Okay.
And we're I think the industry's already accepted that, and they're already on that trajectory, going from 2.5D to multi-chip modules, then chiplets, and then going 3D. So the hardware industry's already known all these things, and they've been talking about it for the past 30 years. So I don't think we'll struggle there. It's really hard to get there.
Okay.
But we can get there.
Yeah.
Right? And that's why this industry exists. We love doing hard things.
Yes.
So that's one. If you're clever, there's enough land. And as long as you can get around some of the regulatory hurdles or geopolitics, there can be enough energy.
Okay.
Cooling does become a bit of a challenge. And this is where having really good design matters. And if you design poorly, and if you don't design for software or developers, you create more problems for yourself. Because then you have inefficient code, and inefficient code forces you to build a larger system and spend more energy.
Okay.
So there's ways.
There are ways. Yeah. I mean, this podcast is about hardware. So we are used to speaking about hardware. And obviously, we all think hardware is going to be the key thing going forward. I mean, you mentioned a lot of things here, 2.5D, 3D, chiplets, heterogeneity. All the buzzwords. What about more specialized microarchitectures? What about lower precision? What about hardware kind of at the system level, better connections between accelerators and so on? There are plenty of dimensions here plenty of knobs we can turn here, right?
So much. I think it's the first time in a long time that metallurgy knowledge is becoming cool again in the industry.
Okay.
Yeah, you kind of have to go there. There's a lot of work to be done on packaging and system integration. I think general purpose computing will always reign king and will always be required, but it's going to come from larger integration of heterogeneous parts.
Okay.
Right. So purely specialized chips have, at least in my view, limited benefit.
Okay.
Because I'm fully expecting a world where things change. Okay. And it's the one thing you always don't count on, that things are changing. Right? So if the workload is getting bigger, if it is changing to try and leverage data better and become more sample efficient, if it moves slightly away from transformers, all the amount of silicon that was built to just support a specific class of transformers is now useless. Right? And there's a limit to acceleration there. But if your thing becomes too big and you spill out of memory, well, you're probably better off just using the general purpose accelerator anyway.
Yeah. Okay. Interesting. I mean, we are seeing companies coming out of stealth or coming to the market with LLM-specific accelerators, but is that the way to go in the short term even? I mean, I know you're kind of a long-term thinker.
Yeah, that's one of the curses of being a founder. You're profoundly optimistic and you're thinking on much longer horizons than it seems natural to.
Than most AI people think in a scale of month to 2 months, I think.
Yeah, I mean, the amount of things. It is interesting though, isn't it? More and more gets packed in shorter and shorter amounts of time. It's completely upended our sense of time because we can't. But getting back to the question, things are changing in ways that seem often surprising. And if you're at one of the AI labs operating in the cutting edge, things are moving even faster. Right? I know some labs that are currently thinking beyond transformers already. They're already asking the question, what do we do next? Right? So there's roughly 30 to 40 trillion tokens of text data out there in the world that are usable for training. Okay. Once you go towards multimodality, that's somewhere between 200 to 230 trillion tokens.
Okay.
So if you kind of follow chinchilla scaling laws, or I don't even know if they're still relevant anymore, but if you roughly follow scaling laws, it tells you how big a transformer can get. Right? What do you do next?
Yeah.
What if you, I think in 2 more cycles of frontier models, we'll probably be hitting it.
There's some talk, or there was a lot of talk when transformers became a thing, about synthetic data and using LLMs to make data to feed into more LLMs.
Yeah.
I'm not sure whether I think this is a good idea or not. I'm leaning towards probably not.
There's a couple of different views, and I don't think anyone knows yet what the right answer is.
Okay.
Right. So there's one view where models get good enough that they start distilling the basic rules that generated that data. And it's sort of the whole Kolmogorov complexity kind of argument. The simplest algorithm that can generate that algorithm is the actual thing that you want that gives the compression limit. If you can find the equivalent for neural networks, you can generate all the data you want. And then you can scale infinitely as long as you have enough energy and land and compute.
Yeah.
So fabs become the limitation over there. They're already kind of a limitation.
Yeah.
Well, not so much fabs, but HBM and CoWoS now.
Yeah.
So if that is solved, I think that changes the argument a lot. And if energy becomes free, just move to the simplest algorithm you can and just scale and go nuts. Right?
Yeah.
But if that doesn't happen, and there have been some studies that have shown that recirculating data, even with different kinds of perturbations or synthetic data, for example, trained on original data sets, end up acting more as noise and degrade the fidelity of the models.
Okay.
And if that ends up being the case, that's problematic. And neural networks already have quite a bit of noise inside of them, which is what helps them regularize. So a little bit of noise is good.
Yeah.
Too much noise is really bad.
Yeah.
And and then there's the other part of it, which is when you are trying to take that model to into an application, you're tending to quantize it, right? Or you're trying to induce more sparsity. When you are quantizing a model, you're actually changing the underlying behavior of the model in ways that you can account for.
Yeah.
So that is something that also needs to be factored in, right? More noise.
Yeah.
So what's the noise threshold of the network that you are currently trying to deploy, and what's acceptable by the end users?
Okay. Tell us about the software situation. I know you one of your positions is you think there's still a lot of play left in software for optimization and so on. What kind of optimizations are you thinking? How many orders of magnitude do you think we can get from out of software? Is today's AI software really that bad?
It's pretty bad.
Okay.
Right. So if you're thinking about just programming on NVIDIA GPUs, you're probably going to do decently.
Mm-hmm.
There's a couple of things that they as a company did ridiculously well. Right. And I don't think the rest of the industry fully appreciates that sometimes. Right. Because everyone talks about GPUs just being a bad architecture.
Yeah.
They're actually pretty good architecture. They're really powerful as long as you do things right.
Yeah.
And if you do things the way that it wants to get programmed, you're going to do pretty well.
Yeah.
Now, could something better be designed? Sure, something can always be better designed. There's always more optimizations to be had. And I think all the GPU companies are somewhat trending in the same direction. So we're a lot of the startups building general purpose accelerators. So where things end up, let's see. But the thing that ultimately dictates success, as it did for NVIDIA, was software. It wasn't the beauty of the architecture, right? Because they weren't designing for other architects to appreciate how beautiful a job they did.
Yeah.
It was developers that needed to get a job done.
Yeah.
Right. So CUDA and PTX and that underlying microarchitecture had to be very well thought out and co-designed. Right?
Mm-hmm.
Because people don't think about this as much because they talk about the cost of hardware. But the cost of hardware is somewhat negligible compared to the cost of developers' time.
Right.
Right. So if you write bad software, you create more bugs, and bug chasing is very time consuming.
Yeah.
Right? And that's cost companies way more than hardware has. Software has always been designed under certain assumptions. Right? The economics have dictated at that time. There was a point where hardware resources were limited. So you needed to give, and hardware was simpler as well. So you needed a low-level language that could allow you to express your thoughts that could map well to that hardware to get that performance out. Right? Performance engineering became an art at this time. As hardware became more complicated and bigger, and problems changed, people had to go higher level. So languages had to get recreated that had higher levels of abstraction. Right? Eventually made our journey from, Fortran and Algol 68 and Fortran to C and Java and so on and so forth. And then eventually we landed on Python, and that became the developer's tool of choice for AI because it was easier to think in.
Yeah.
Right? Python was never meant as a production language.
Yeah.
Right? But it's what we have. It's what we're using. But there's a massive mismatch between the abstraction that Python uses and the programming model it has and the tools that we're using on the hardware side. Right? That is a very complicated job for people to traverse. And if you have things underneath PyTorch, like NumPy, you have CUDA, you have other things. Now they have a Triton backend that talks to CUDA. There's a whole bunch of other libraries. People are building their own compilers. Every time you do training, you have a whole separate other set of libraries you need to call, and then you need to take that, put it into a package, and then you deploy it, and you have a whole other set of libraries to do. The number of things that a developer needs to now keep in mind to make AI work is ridiculous.
Yeah.
Right? We should have better things. We kind of deserve to have better things.
We deserve nice things, yeah.
You suffer enough for your job, but the least we can have is something decent to work with.
I mean, this is complex software infrastructure that on an area that's still very immature, relatively speaking. I think just need to catch up a bit, right?
Absolutely. For the things that we're talking about building in terms of AI and the talk of AGI, we should be doing better than primitive tools. Right? It feels like you're trying to find a Michelangelo and give him a chisel and a hammer and say, go carve me David. But it would be far better to just use the tools we have, like good CAD tools and GPUs, and kind of just simulate the thing and give it to a machine that can churn those out at scale.
Yeah.
Then that would be kind of interesting. Then you've unlocked, thousands of more people to do interesting work.
Yeah.
That's sort of the rough analogy. Give better tools, give more capabilities, and you have less things to do when it comes to bug finding. Plus, if you have better tools and they're designed for the kind of environment you're going into, it's easier for you to get performance out. And performance really matters. I don't think I've ever come across a single person in the world that said, I have enough compute.
Right, yeah.
Right. So there's a lot of early work in computing was driven by the paper that Feynman wrote, There's Plenty of Room at the Bottom. Right. And correlate to that, which is there's plenty of room at the top.
Okay.
Right. And it basically tells you the importance of co-design, the importance of domain-specific architectures and languages. And if you actually do things right, there's somewhere between 2 to 3 orders of magnitude performance available from good software.
So 1,000x from good software, that would be awesome.
I think that's the ceiling, but I think it's achievable as long as things are done right. That's the caveat. If you do things idiomatically, you're not always going to get there, but if you do things well, you just might.
Okay. I like your optimism. I think we already kind of spoke a little bit about where you think models are going bigger, but can we optimize for less compute by evolving model architectures, and how much can we squeeze out on that front?
I think that's a bit unknown at this point, but so if you increase the context window in an LLM, the impact that you can get is roughly an order of magnitude in equivalent compute.
Okay.
So you've prevented yourself from going 10x bigger, but you have a similar impact because you have more context.
Okay.
So there's things like that are really interesting about it. Finding ways of overtraining, for example, and then finding new ways of doing things. Like those will make a difference. Right? Ultimately, it's about how well you can compress and store information and then generalize so you can retrieve it when you're serving an answer. So I have to think a little bit more about it, but I think given what I've seen just happen in LLMs over the past 5 years, I can't believe it's been 5 years. No, it's been 8 years. Yeah.
Oh, time flies. Yeah.
I think there's roughly 2 orders of magnitude from better architectures that can be found.
Okay.
And if you do that, you don't have to go as big
Okay.
because you're becoming more sample efficient.
Yep.
And that's going to make a huge difference.
Yeah.
Just do the math there.
Yeah.
1000x from really good software. Let's assume we're being totally optimistic. 1000x. Somewhere about 100x from model architectures. Based on existing roadmaps and hardware vendors, we're currently looking at about 1000x from there over the next 10 years.
Yeah.
Planned data center build-outs, it's another 10x, right? So we've got 9 orders of magnitude that we can find.
Okay.
Yeah.
Only 10x from building more data centers? I was going to say only 10x, but that still means building 10 times the amount of data centers that we have today. We spoke about, you said land and geopolitics and blah, 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 but do you think 10x is feasible?
I didn't do so well in geography at school, so I don't really know.
Okay.
I'm assuming that the people that are planning the data centers know what they're talking about.
Yeah, okay. That's kind of an industry figure then, I guess.
Yeah, that's the word on the grapevine.
What about tricks like that aren't really model architecture stuff, like compression and sparsity and quantization and other kind of techniques we have in our toolbox? Think we can gain a little bit there?
Oh, yeah. So I was talking about training, so we're getting to inference now.
Yeah.
Yeah, there's a lot more tricks when it comes to inference. So quantization, pruning, compression, those are things that we've been talking about for the past decade.
Yeah.
Longer, maybe. Yeah, definitely longer. At least when it comes to neural networks. There's other tricks as well, knowledge distillation, right?
Yeah.
So instead of do a teacher-student kind of setup, take a big model, distill that knowledge into a smaller model. It'll retain most of that. You can do a little bit of extra fine-tuning or transfer learning there, and then you're good to go. There's also moving towards mixture of experts models that prevents you from also growing as big. And it's also very good for inference, because if you have 8 experts and you're only having 2 of those experts active at a time, you're saving a lot of compute, right?
Yeah.
So the combination of all of those things can save you many orders of magnitude. And then there's other optimizations you can do to actually map those workloads well to hardware, right? But again, if you end up in a world of heterogeneity, for example, or if you want to use something other than the same GPUs that everybody else is using, or you have internal silicon programs at one of the companies and you want to use that hardware, you want to be able to do optimizations for those, but that requires you generally understanding hardware as well, which makes that really hard.
Yeah.
So good example of this that has been floating around is flash attention.
Yeah.
Like flash attention has been all the rage. But every time a new vendor goes to a developer to convince them to use their hardware, one of the questions is, do you run flash attention?
Yep.
The answer cannot be true. It can't be yes.
It can't be?
It can't be, because flash attention 2 and flash attention 3 were very optimized and designed for running on. Flash attention 2 was designed for running on Ampere, and then flash attention 3 was designed to run on the Hopper.
Yes. Okay.
Right? So we've known this for a long time throughout the industry, and somehow we keep forgetting it. But a mismatch between a programming model, execution model, and the underlying hardware leads to bad performance. You have to get those 3 right.
Yeah.
Right? Otherwise, developers can't get performance out. It's like trying to map CPU code over to a GPU. It just won't work.
Yeah.
Well, it can work, but just very badly.
Yeah. Yeah.
Right? So you're leaving a lot of performance on the table there. That's part of what's happening in Flash Edition 2 and 3 as well. Those are optimized kernels for running on specific GPUs. So if you run that implementation on other hardware, it's not going to do well. Right?
Yeah.
So you need to have a way of distilling that semantic up into something that's a bit more general, and then do that optimization again for different hardware. And that has to roughly get automated.
Yeah.
Right? That is the real problem that exists today. And if we do end up in a world of heterogeneity, and I really think we're not far from it, because we've had different kinds of heterogeneity already, but we're very close to getting to a world that is scary. or scarier.
How hardware aware do you think people who write Python code are in general? You spoke about flash attention there. If they didn't know it was kind of a GPU only thing, do you think we can do better on educating people writing at that level about what is hardware specific about heterogeneous hardware? Or do you think they shouldn't have to know? They should just press a button and off it goes?
Is it possible? Probably.
Okay.
I think most things are possible, just people don't want to do them.
Okay. Fair enough.
I think in an ideal world, developers shouldn't have to think or know everything about hardware.
Yeah.
Right? That's our job as computer builders, to create good abstractions that allow people to be productive and get the things that they want to get done, and not be aware of the underlying microarchitecture to the point that's the only way to get things done. Right?
Yeah.
People shouldn't have to go write assembly code.
Yeah.
We left that world for a reason.
Yeah. Hopefully we've left it. I think there's still a lot of AI folks down there in the weeds.
Yeah. They shouldn't have to be. I mean, probably the lowest you should end up having to go to is C. That is for very specific things. But even writing CUDA is hard for a lot of people. There's very few performance engineers in the world. There's less than 1,000, I would say, that can really do a good job. And most performance engineers specialize on specific platforms or tools. So if you go to a different shop if you're an OpenCL person and you go to a CUDA shop, are you going to be really happy? Yeah. Or if you're a CUDA person that has done CUDA your entire life and you go to a place that is doing OpenCL work, or you want to go towards AMD GPUs and you have to relearn the whole ROCm stack and figure out every single thing that's going on there, or if you want to go to Google working on TPUs, they have a very specific way of doing things. That knowledge doesn't always translate super, super well. There's a specific way of thinking and writing code that you get trained with, that you just accept.
Mm-hmm.
Right? It's hard, and we need to find a whole new way of doing things now. Because there is more hardware out there in the world that is just not getting used. And if we want to get to the point where AI is in abundance and it's affordable and everyone benefits from it, you have to unlock hardware.
Yeah.
And unlocking hardware doesn't mean just from one vendor. It means from a lot of vendors. And then we can kind of think about getting to the ideal case of saturating compute.
Yeah. Okay. Tell us a little bit about Lemurian Labs, what you guys are working on, and where do you fit into all of this that we're talking about?
Yeah. Lemurian's a magical place where naughty people like me and a whole lot of others think about solving hard problems. And one of the hard problems that we've chosen, of course, is bringing down the overall cost of AI by about 1,000x. Okay. That's sort of how we set our target, because we like being ambitious.
Mm-hmm.
And, as you well know, we started as a hardware company.
Yep.
And we thought, let's just go build hardware, and that's going to solve the problem. And while we were doing that, we designed a really cool architecture, at least so we thought it was really cool, and it was general purpose, good training and inference. We created a number format, did all that work. And then I was thinking about where we end up and the buying cycle for all of our would-be customers, and why existing second sources in the market haven't gained adoption and what makes us different.
Yeah.
All of those things led us to thinking more about software. And when you think about the models and you think about where they're going to go, and you look at the roadmaps from a lot of the existing frontier AI model companies, and you look at the amount of compute that's going to be required on a daily basis to serve these models, I think my calculation ended up being about 10 to the 32 flops on a daily basis within 10 years.
Okay.
You can't get that by having homogeneous or regular architectures. So you end up with that world of heterogeneity no matter what.
Yeah.
Right? There's that adage that's been going around for a couple of decades: everything that happened in mobile will happen in the data center. Well, now that's about to be very true.
Yeah.
And we know one thing from the mobile world: SoCs are really hard to program.
True.
Right? Each of those special function units or accelerators in it have a different programming model. Right? I used to have to program the Jetsons from NVIDIA or the RBs from Qualcomm when I used to work in robotics. And most of the people on my team could not target the rest of the platform because they didn't know how.
Wow.
Right?
Okay.
And these people are people I thought were relatively good engineers.
Okay.
Like if you're working in the robotic space and you're working in embedded, you have to be a pretty good engineer. So if they couldn't target, how is the rest of the world who's not as good an engineer, but is a really good ML engineer, going to be able to get performance out of these things?
Okay.
So you have to think about sort of unifying the programming model and execution model and creating a way that you can actually scale with cluster size. So it's entirely new problems that compilers haven't had to solve, but are now there.
Yeah.
Right? Like, for example, the things that we've used for programming single CPUs and GPUs is very different from the thing that we need to program 1,000 GPUs or 100,000 GPUs.
Yeah.
And those are the skills that we're talking about right now.
Yeah.
Right. So you have to rethink software in a very large way to be able to get the most out of that world. Right. Do you really need 100,000 GPUs or are you just using it poorly?
Yeah. What's the utilization like?
Yeah. I've seen a few AI companies where they're doing training runs and they're less than 15% utilization.
Sounds pretty bad even compared to what I've heard. Yeah, that's terrible.
It is.
What's just expensive GPUs basically not doing much.
Exactly. So if you're going to be spending that much on GPUs, you might as well spend a little bit extra effort and just get most out of them.
Right? There's another 85% there up for grabs.
You'll never get the 85%, but you can at least get another 50%.
Yeah, right.
And we want to make it easier to do that on multiple different platforms. Right? So you write your PyTorch code. Everything else that's underneath, and if you do want to have the capability to write custom things for yourself in case PyTorch doesn't support it as well as you want, or you're super smart and clever and you want an interface to do that, we want you to have that.
Okay.
Right? And we've created this universal interface, or like it's a pseudo instruction set virtual machine that's also part of the compiler as one of the IRs. Weird way of putting it. Three different terms. But you target everything down to this, you express everything in that, and then you have your hardware-specific code generators that plug underneath that. And then you have a dynamic runtime that can do data and task placements on different kinds of hardware given that cost model. Right? So you don't have to think about, hey, this thing is, very single-threaded, so I'm going to put it in this particular place where I really care about latency, so it's going to go on a CPU. This part has, a particular kind of way of expressing things. So it fits very well in the data parallel model. So I'm going to put it there. I have certain kinds of things that will perform really well on, say, an NPU instead of a GPU. So I want that to go there. But I also need to coordinate that and maintain coherency and a whole bunch of other things that are really ugly to think about in this world. But you need to do that. And the way we've been thinking about this is not, we're the smartest programmers in the world. No, we just have the experience of designing and co-designing hardware, so we know where things are going to end up. And we built these simulation models for different kinds of hardware to figure out where we want it to go architecturally. And we were thinking about the programming models and execution models for each of those. And we stumbled across a realization that those can actually be unified. And then if you think about what are the things that need to be true at different stages through the compiler or the runtime to be able to map well, and you keep building up and you keep thinking about how to generalize this, and you build those into patterns that you can build up into abstractions higher and higher, you kind of get to a point where you're like, okay, I have a general way of doing things now.
I mean, yeah, general sounds very ambitious to me at this stage.
Yeah, you kind of need a moonshot.
Yeah.
And I don't think anything other than a moonshot will fit for this world.
Yeah. So which levels are we innovating at here? I mean, you mentioned intermediate representations. Is this a fancy compiler, or are you taking on more than one layer of the stack with this new platform?
Yeah. So basically PyTorch down to our virtual machine is where we'll work. And then we have our dynamic runtime.
Okay.
And the way we partner with all the hardware companies is you now have a single stack that allows you to be more discoverable by developers. It's easier for them to think and do their work. the hardware-specific code generator that you're building can plug into that, and we'll give you the interfaces and all the different stuff that you need to hook into it, and then make you help you become discoverable in that stack for developers. So you're doing, say, import PyTorch, import Lemurian, then you do PyTorch with Lemurian backend, and then you specify the hardware you want to run on. And with that, you can get performance down on your hardware. Now, it'll be better performance than what you would have gotten if you just ran PyTorch natively.
Yeah.
Right. And that's good for most developers. But for folks that really care about performance and they want to get more out of it, there is an API which they can use to do custom work.
Okay.
Right. But as every single person listening to here, at least I think might know, is reading general compilers generally means you're losing performance somewhere. So how the hell are you talking about, performance on heterogeneous systems with a general compiler?
Yeah.
Something's amiss. There's a way of actually expressing the organization of the hardware and putting that in as an intrinsic that allows you to carry in certain kinds of information that helps with that performance. And that's part of the magic.
Okay. So my understanding is that MLIR had some of these types of features, or is this something that is part of your own secret sauce?
It's part of our own secret sauce.
Okay.
Yeah, we basically end up having to rethink the majority of things because existing tools did not work for us. We tried really hard to make it work for us.
Okay. Jay, are you still making the chip? Are you still a hardware company as well, or what are your plans on that front?
For the moment, no.
Okay.
Yeah, it doesn't make sense to build a chip right now. That's something we can talk about future point in time, but right now really focus on the software because there's enough hardware companies out there. There's a lot of money that's been put into hardware companies. If you're selling hardware, you need at least 2 or 3 generations of design wins with working software and showing that you can run all those workloads before you're even in consideration.
Mm-hmm.
And all your would-be customers are building their own silicon as well.
Yeah.
And they've already planned 2, 3 generations out. So you need to be provably better than what they're building for them to consider you.
Yeah.
Right? And if you're fighting for the general purpose market, you need to show that you have the same robustness and ecosystem or breadth as NVIDIA does.
Yeah.
Right? Companies like AMD and Intel have struggled because they know that it's really hard to build that ecosystem out.
Yeah.
Right. But if you can have a single software stack that all the semi companies get behind, it allows you to build that ecosystem and share in the costs so that you now become more available for all the different people that want to use that hardware.
Okay.
Right. So you don't have to learn a new way of programming every single time you want to shift over to something.
Okay. Yeah.
Right. So given that, it didn't make sense to go raise $500 million and be like, oops.
Oops.
Yeah.
Yeah. Okay. It makes sense to me. It definitely does. With the software platform then, is this something that is still in development? Are you up and running? Can people come try you guys out, or what stage of readiness are you?
Yeah. Right now, like one of those things about building compilers is it's hard work. It takes time.
Yeah.
Right. And the last thing you want is to prematurely release a compiler and have it be buggy.
Of course.
Right.
Yeah.
Nobody wants a brittle compiler. So we've got a full cut through the stack running that can ingest a couple of the PyTorch workloads and integrates into Torch Dynamo, and it can run on a couple of the backends that were specified so far, at least. There's a little bit more work. Probably in 6 months, we'll have what we're referring to internally as a 1.0 that we can then get people to start sampling and using.
Mm-hmm.
That'll be available in a sandbox environment.
Okay.
And probably about another 4 months from there, it'll be available with backing from one of the hardware companies that we're working with and on one of the clouds.
Okay.
And then we'll go for general availability later on.
Okay. Jay, this is a massive task. Best of luck.
It is.
Good luck with everything.
But fortunately, I have an amazing team.
Yeah.
And make it easier.
Yeah, absolutely. I think it's a great place to leave it. Thank you so much for the interesting chat, and let's speak again soon.
Absolutely. Thank you for having me.
Thank you very much to Jay Dawani, CEO of Lemurian Labs, for the interesting conversation. This episode of AI with Sally was brought to you by Lemurian Labs. Thank you very much, Lemurian, for sponsoring us. That brings us to the end of the episode. Please tune in again next time to hear more news and views on AI, machine learning, and the technologies that enable them. If you're listening to this on the podcast page at eetimes.com, links to articles on topics we've discussed are shown on your left. AI with Sally is brought to you by Aspen Core Media. The host is Sally Ward-Foxton and the producer is James Eade. Thank you for listening.